Hi, my name is Calvin, and I'll be going through this question that was posted by Bill K today, actually, so 6/10/21. So first we highlighted all the relevant information and all the quantities that they gave to us. So we see 25 mils of Na2CO3 is important. It's neutralized with 22.4 mils of 0.1065 moles of HCl. And then we see in the next step there's 50 mils of Na2CO3 solution added to this amount of PbNO3 solution. And after that was filtrated, the excess Na2CO3 is neutralized with this same acid, meaning this acid right here, this 0.1065 molarity hydrochloric acid. And then according to this, calculate the concentration of lead to nitrate, and they gave us the molar mass as molarity and grams per liter. So they want the same answer in two different units, okay? So we split this up into two phases. So first they have the acid-base titration. So we see that solution 1, this was given to us from the question, 25 mils of Na2CO3. They didn't give us the molarity. Next we have this right here, so I just rewrote this, 22.4 mils of 0.1065 molarity HCl. So now we have the two solutions. We're going to use this equation right here. And what this means is the volume of solution 1 times the molarity of solution 1 equals the volume of solution 2 times the molarity of solution 2. And the way that you get that is, let's look at the units associated with them. So V1M1 equals V2M2. Well, if they have different volumes and different molarities, how could they equal each other? It's because the units end up canceling each other out. So volume turns into liters as its unit, times molarity, which is moles per liter, equals, same thing here, liters times moles per liter. So what happens is the liters all cancel out, and you end up getting the same moles. Okay, so what this equation tells us is the number of moles should be equal to one another. Okay. So let's do the math here. Let's plug in everything that we know. We convert this milliliters to liters by moving the decimal over 1, 2, 3 times. So 0.025 liters times moles over liter, right? Because we don't know what molarity is, equals, this is all given to us, right? So we convert this to liters, we plug this in, and then what we did was we just divide everything by 0.025 liters, moles per liter. And I just rewrote that right here. So what ends up happening is this liters cancels out with this liters cancels out with this liters, and this mole cancels out with this mole. So all you're left with is a numerical value. So the molarity of solution 1 is this number right here, which we just put here. And again, molarity still has a unit associated with it, which is moles per liter. And then now we also have this reaction equation, right? So it's important to make sure that you balance it correctly because you may or may not refer back to it to use its molar ratio. This question was nice in that all the ratios are 1 to 1, which we'll see later on, but in other cases it might not be. So you might have to multiply by 2. Sometimes you might have to divide by 3 or something like that, depending on what the molar ratio is and what you're trying to find. Next, we have the phase 2. So it's a precipitation titration. So same thing, it's doing a titration, but this time instead of using an acid base as a reaction, we're doing a precipitate reaction as the titration indicator. And then after that, it's followed by neutralization, also known as quenching. So they gave us the quantity of Na2CO3 which was used, but this time we know how many moles are present because we calculated for the molarity of it earlier. And then we're going to add 25 mils of PbNO3. So this one we only have the volume, but we don't have the molarity. So that's what we're going to have to calculate for later on. So again, we write out the equation, and this is the solid that we're looking for. This is the precipitate that we're looking for. The question said that this is Na2CO3 is an excess. That's why we have to neutralize it afterwards. Therefore, by definition, this is the limiting reagent. So let's start doing the math. So we want to know how many moles of Na2CO3 we had to begin with. So 50 mils of Na2CO3 is converted to 0.05 liters times the molarity that we calculated for earlier, which is right here. equals this number of moles of Na2CO3. So this is our starting value of Na2CO3. Next, we want to calculate how much was left over, and we do that by calculating that neutralization reaction at the end. So 14.8 mils of HCl was used to neutralize the remaining Na2CO3. So again, we have this. We just convert this into liters. We were given this earlier in the question, and then this is the numerical value that we get for it. So because Na2CO3 and HCl have a 1-to-1 ratio, which we established in this equation right here, notice the coefficients is 1 to 1. So sometimes it could be 1 or 2, depending, or like maybe like 3 to 2, depending on what the equation is and how you balance it. It could be different, but again, they were nice to us and they gave us a 1-to-1 ratio. So because it's a 1-to-1 ratio of Na2CO3 to HCl, this numerical value of HCl is going to be the same numerical value of Na2CO3. So that's why it's important to balance the equations properly. So now what we do is we put this starting quantity and this ending quantity into this equation right here. So start minus end equals the amount of reacted Na2CO3. So that makes sense, right? Well, we had to begin with minus what was left over. That difference tells us how much of that Na2CO3 actually reacted. So once we subtract these two values, we get this. So 0.003195 moles of Na2CO3 reacted to form this precipitate. Next, again, we have a 1-to-1 ratio, Na2CO3 to PbNO32. So 1, 1. Those are the coefficients, right? So again, same numerical value. We're just going to put this down here. And this is the number of moles of PbNO32 were in that reaction. And because they gave us the volume of that, now we can calculate for the molarity. So 25 mils converted to liters, 0.025 liters. And then again, molarity equals moles over liter. So we plug this number in here, moles divided by the number of liters. And this is our molarity value. So if we go back up to the question, it asks us to give it to us as molarity and as grams per liter. So we're not done yet. We have this, that's good. But now they want it given to them in grams per liters. So what we're going to do is we're going to put this right here, right? Because 0.1278 molarity is the same as moles per liter. So 0.1278 moles per liter times this molar mass, which again they gave to us, 331.2 grams per mole. We put this in here, 331.2 grams per mole, because we want it to be given to us in grams. In this little 4-quadrant system that we have right here, grams is going to be in the top right, and then these two units that will cancel out will be across from one another. So one always has to be in the numerator, one always has to be in the denominator, and then the liters is left over and the grams is also left over. So after we do this math, right, you plug this in, 0.1278 times 331.2, you get 42.33, and then you keep the units, right, grams per liter. So we'll cross these out, and these guys are what are left. So yeah, this is how you do these types of problems, is paying attention to stoichiometry, making sure that your equations are balanced correctly, making sure your units are correct. So this one we deduced that we have to get from moles to grams because that's what it wanted, right? From moles or molarity to grams. So then we just remember the different relationships that each of these units have with one another. So they gave us a hint in the problem that we're probably going to use this as a conversion factor later on, and then we were able to finish up the math. So yeah, if you guys like this video, please let me know. I'm also on Wise Answer if you guys need chemistry tutoring in the future. Feel free to reach out. Thank you guys.